For decades, American observers meticulously followed every technological advancement emerging from factories and laboratories around the world. Engineers, specialized scientists, and materials experts dedicated their entire careers to studying metals, alloys, and processes that could offer strategic advantages in aerospace and industrial applications. But nothing, absolutely nothing, prepared them for what they would witness when a single industrial process completely revolutionized how metal alloys responded to the extreme temperatures found in high-performance environments and critical operations. This is the story of how materials science transformed the impossible into reality, and how a seemingly simple process forever changed the course of modern engineering. To understand the magnitude of this discovery, we need to go back in time and understand the fundamental problem that has plagued engineers and scientists since the early days of aviation and advanced aeronautical applications. When the first jet engines began to be developed in the 1930s and 40s, engineers quickly realized they were facing an invisible and relentless challenge: extreme heat. Temperatures inside the combustion chambers and around the turbine blades reached levels that caused conventional metals to melt like butter under the scorching desert sun. Steel, the material that had been the backbone of the Industrial Revolution and global technological development, simply could not withstand the brutal conditions imposed by the new era of jet propulsion. Early aeronautical engineers worked in temperatures that rarely exceeded 1,000 degrees Celsius, and even then, they faced catastrophic failures with alarming frequency. Turbine blades disintegrated mid-flight, engines failed without warning, and aircraft faced serious safety problems because the available materials simply could not maintain their structural integrity under such severe conditions. It was like trying to build a sandcastle during a storm. Every attempt to increase engine power, every effort to improve the performance of advanced aircraft, ran up against the same insurmountable limit: the inability of metals to maintain their mechanical properties when exposed to the intense heat generated by high-speed fuel combustion. Before we continue on this fascinating journey through the history of metallurgy and industrial innovation, I'd like to invite you to subscribe to this channel and leave a comment telling us what time you're watching this documentary. Your support is essential for us to continue bringing you incredible stories about science, technology, and innovation that have shaped our modern world. During the 1940s and 1950s, scientists from various nations worked intensely to develop alloys that could withstand higher temperatures for longer periods. Laboratories on different continents worked day and night, testing combinations of metals that included nickel, chromium, cobalt, tungsten, and dozens of other elements. Each new alloy promised to be the ultimate solution, but reality always proved crueler than optimistic predictions. The alloys failed, not gradually and predictably, but suddenly and catastrophically. A turbine blade that seemed perfectly functional one moment could disintegrate the next, turning a multi-million-dollar engine into useless scrap and, worse still, endangering the lives of pilots and crews. The fundamental problem wasn't simply the absolute temperature, although that was certainly a critical factor. The real challenge lay in the intense combination of high temperature, extreme mechanical stress, and the corrosive environment created by the combustion gases. Imagine a piece of metal being simultaneously heated to temperatures approaching its melting point, subjected to centrifugal forces attempting to tear it from its assembly, and constantly bombarded by aggressive chemical gases. This was the working environment for turbine blades in high-performance jet engines. And as if that weren't enough, these components needed to maintain their shape and strength for thousands of hours of continuous operation, without failing, without deforming, without losing efficiency. Metallurgists of the time knew that the answer lay somewhere in the vast periodic table of elements. They knew that certain combinations of metals could, theoretically, create alloys with superior properties. Nickel, for example, demonstrated excellent resistance to oxidation at high temperatures. Chromium formed a protective layer that prevented corrosion. Cobalt maintained its strength even when heated to red hot. Tungsten and molybdenum added hardness and resistance to yielding. But simply mixing these elements together in a crucible did not necessarily produce an alloy with all these desirable properties working in harmony. In fact, it often produced the opposite: alloys that were brittle, difficult to manufacture, or that failed in unpredictable ways. It was in this context of frustration and seemingly insurmountable challenges that the first generations of superalloys began to emerge. These remarkable materials were primarily based on nickel or cobalt and incorporated carefully calculated amounts of other elements to create a metallic matrix that could withstand temperatures that would render conventional steels completely unusable. The first superalloys represented a genuine leap in materials science, allowing jet engines to operate at temperatures hundreds of degrees higher than anything previously possible. But even these marvelous alloys had their limits, and engineers continued to push for ever greater performance, ever higher temperatures, and ever better efficiency. What scientists discovered, through years of meticulous research and countless experiments, was that the internal structure of the alloy was as important as its chemical composition. It wasn't enough to have the right elements in the right proportions. The way these atoms were organized in three-dimensional space, how microscopic crystals formed and interacted with each other, and the presence of specific secondary phases distributed throughout the metallic matrix, all of this determined whether an alloy would be a brilliant success or a spectacular failure. It was like discovering that having the right ingredients wasn't enough to make a perfect cake. The oven temperature, the baking time, the order in which the ingredients were mixed, all of this mattered immensely. American technical observers followed these developments with growing interest, understanding the strategic implications of each advance. An alloy that could operate just 50 degrees hotter than the previous one meant more powerful engines, faster aircraft, greater range, and better performance at altitude. In practical terms, this could mean the difference between technological superiority and operational limitations, between success and failure in critical missions. Every fraction of a degree mattered. Every small improvement in creep resistance, fatigue resistance, and oxidation resistance translated into measurable technical and operational advantages. During the 1950s and 1960s, the development of superalloys accelerated dramatically. Alloys with names that sounded like secret codes, alphanumeric combinations that concealed carefully guarded chemical compositions, began appearing in technical reports and scientific publications. Each new alloy represented hundreds or thousands of hours of laboratory work, destructive testing, microscopic analysis, and iterative refinement. Scientists learned that adding small amounts of elements such as titanium, aluminum, niobium, and tantalum could create microscopic precipitates that strengthened the metallic matrix in surprising ways. These tiny particles, invisible to the naked eye but clearly visible under electron microscopes, acted as barriers that prevented the movement of crystalline defects, keeping the alloy strong even at temperatures where other metals would become mushy and malleable. But there was a persistent problem that continued to plague the brightest metallurgists of the time. The alloys they developed in the laboratory, with impressive properties and exceptional performance in controlled tests, often behaved completely differently when manufactured on an industrial scale. The conventional casting process, where liquid metal was poured into molds and allowed to solidify, created a polycrystalline structure with millions of tiny, randomly oriented crystalline grains. The boundaries between these grains, called grain boundaries, became preferential pathways for crack propagation and weak points where deformation could begin at high temperatures. It was like trying to build a strong wall using millions of small, poorly fitted bricks instead of large, well-fitted blocks. Engineers tried various approaches to solve this fundamental problem. They developed elaborate heat treatment processes that attempted to homogenize the grain structure. They experimented with forging techniques that were supposed to refine and align the grains in favorable directions. They added chemical elements that were supposed to strengthen the grain boundaries. But each partial solution brought its own problems. Prolonged heat treatments were expensive and did not always produce consistent results. Forging was difficult to apply to components with complex geometries such as turbine blades with intricate aerodynamic profiles. And the chemical additives that strengthened grain boundaries often weakened other important properties of the alloy. It was during this period of intense research and experimentation that radically different ideas began to emerge about how to manufacture superalloy components. If the fundamental problem was the presence of millions of grain boundaries acting as weak points, then the logical solution would be to reduce the number of grains or, in an ideal scenario, eliminate grain boundaries altogether. This idea seemed almost absurd at first glance. How could anyone manufacture a metallic component the size of a turbine blade, tens of centimeters long, composed of only a few giant crystalline grains, or ideally, a single continuous crystal? The very physics of metal solidification seemed to make this impossible. But the history of technology is full of examples where the impossible has become routine, and this would be another one of those stories. Visionary scientists in different parts of the world began exploring solidification processes that could control with unprecedented precision the formation and growth of crystals during the cooling of molten metal. The concept was elegant in its simplicity, but incredibly challenging in its practical execution. If you could initiate the solidification process at a specific point and then carefully control the direction and speed at which the solid-liquid boundary moved through the material, you could theoretically make a single crystal grow continuously, consuming the entire volume of the component. The process that eventually emerged from this research became known as directional solidification, and its most advanced version, capable of producing single crystal components, represented one of the most impressive achievements of modern metallurgy. The basic idea was deceptively simple. Create a very steep and well-controlled temperature gradient so that solidification occurs progressively, always moving in a specific direction. Imagine a ceramic mold containing liquid metal being slowly removed from a hot furnace and entering a cold region. The interface between the still liquid metal and the already solidified metal gradually moves along the mold, and if the conditions are exactly right, the crystals will grow in elongated columns parallel to the cooling direction. But transforming this elegant concept into a practical and reliable industrial process required years of hard work and constant innovation. Engineers needed to develop special furnaces with extraordinarily precise temperature control. They needed to create ceramic molds that could withstand molten metal at temperatures exceeding 1,500 degrees Celsius without disintegrating or chemically reacting with the alloy. They needed to determine the exact cooling rates that would allow the growth of single crystals without the formation of unwanted defects or grains. And they needed to figure out how to initiate the crystallization process so that only a single crystal with the ideal crystallographic orientation would begin to grow. The solution to this last challenge was particularly ingenious. The engineers created what became known as a grain selector, a section of the mold with a special geometry that forced the multiple crystals that naturally began to form at the base to compete with each other. As these crystals grew through a helical or spiral passage in the mold, only those with the most favorable crystallographic orientation were able to continue growing, while the others were blocked and eliminated. When the molten metal finally reached the main cavity of the mold that defined the shape of the turbine blade, only a single crystal persisted, and this crystal then grew continuously to fill the entire volume of the component. When American observers first saw the results of this process in action, their reaction was one of utter astonishment. Here were metallic components that defied all conventional rules of metallurgy. Turbine blades that, when examined under specialized microscopes, revealed a continuous crystalline structure without a single grain boundary along their entire length. The implication of this technological achievement was immediately obvious to anyone with knowledge of materials science. Without grain boundaries to serve as paths of weakness, these single crystal components could operate at significantly higher temperatures than their polycrystalline counterparts. Creep resistance, the property that determines how much a metal deforms over time under constant load at high temperature, improved dramatically. Initial tests confirmed what the theory predicted. Monocrystalline components manufactured with the same alloys used in conventional components demonstrated the ability to operate at temperatures 100, 200, even 300 degrees higher before showing signs of failure. To put this into perspective, a 200 degrees Celsius increase in operating temperature allowed jet engines to be designed with significantly higher thermodynamic efficiencies. This translated directly into greater power, better fuel consumption, greater aircraft range, and superior performance in virtually every important metric. But the benefits didn't stop there. In addition to superior resistance to high temperatures, single crystal components also demonstrated anisotropic mechanical properties that could be exploited in intelligent ways. Because the crystal had a specific crystallographic orientation, its properties varied depending on the direction. Engineers learned to orient the crystals so that the directions of greatest strength were aligned with the directions of greatest stress in the component in service. It was as if they could customize the material properties to perfectly suit the specific demands of each application. The industrial implementation of this process, however, presented formidable challenges. Each single crystal turbine blade had to be cast individually, a process that took many hours and required extremely precise control of multiple variables. The initial success rate was low, with many castings resulting in defective parts that had to be discarded. The costs were astronomical compared to conventional methods. But for military applications where performance was absolutely critical and where technological advantage could mean the difference between life and death, between mission success and failure, these costs were considered justifiable. Over the decades that followed, the manufacturing process for single crystal components was continuously refined and improved. Computational modeling techniques allowed for increasingly accurate predictions of how the metal would solidify under different conditions. Automated control systems improved consistency and success rates. New mold designs and grain selectors increased reliability. And the accumulated knowledge about which alloy compositions performed best in single crystal form led to the development of successive generations of increasingly capable superalloys. But the story doesn't end with single crystal components. The quest for even greater performance led scientists to develop advanced ceramic coatings that could be applied over these single crystal superalloys to create thermal barrier systems. These coatings, typically composed of yttrium-stabilized zirconia, created an insulating layer that protected the underlying metal from the direct flow of hot gases. With these coatings in place, the actual surface temperature of the alloy could be kept hundreds of degrees lower than the temperature of the gases flowing over it. It was like creating an invisible heat shield that allowed engines to operate in conditions that would have instantly destroyed unprotected components. Modern thermal barrier coating systems are multi-layered engineering masterpieces. First, a metallic bonding layer is applied to the surface of the single crystal superalloy. This layer, usually an McRly alloy where M can be nickel, cobalt, or a combination of both, serves multiple purposes. It improves adhesion between the metallic substrate and the overlying ceramic coating. It also forms a slow-growing aluminum oxide layer at the interface that protects against oxidation and corrosion. And it partially compensates for differences in thermal expansion between the metal and the ceramic, reducing stresses that could cause coating delamination. On top of this bonding layer, the ceramic thermal barrier itself is deposited using sophisticated processes such as electron beam physical vapor deposition or plasma thermal spraying. The resulting microstructure is highly controlled, with a specific porosity that reduces thermal conductivity while still maintaining sufficient mechanical strength. More advanced versions incorporate a columnar structure that allows some deformation without fracture, accommodating the inevitable thermal stresses that occur during heating and cooling cycles. Observers who witnessed the complete evolution of this technology, from the first conventionally cast superalloys to modern single-crystal components with multiple layers of advanced coatings, saw a transformation in its effectiveness that seemed almost magical. Engines that would have been considered impossible just a few decades earlier now operated routinely under conditions that would have seemed fantastic to the pioneers of jet aviation. The temperature of the gases at the turbine inlet, a critical parameter that determines the thermodynamic efficiency of an engine, had increased from less than 1,000 degrees Celsius in the first jet engines to more than 1,700 degrees Celsius in the most advanced designs. But the true genius of this unique industrial process lay not only in its ability to produce components with superior properties. The most profound transformation was in how it completely changed the jet engine design paradigm. Before directional solidification and monocrystalline components, engineers were forced to design within very restrictive material limitations. Now, with materials capable of withstanding extreme temperatures, they could explore designs that maximized thermodynamic efficiency without compromises dictated by material limitations. It was as if someone had removed invisible chains that had been limiting creativity and innovation for decades. The impacts of this metallurgical revolution extended far beyond the military applications that initially motivated its development. Commercial aircraft engines benefited enormously, becoming more fuel-efficient, more reliable, and capable of higher power outputs. This allowed for the development of larger and more economical commercial aircraft, democratizing air travel and connecting the world in ways that would have been impossible with previous technology. Gas turbines for electricity generation also adopted these technologies, increasing their efficiency and reducing emissions. Even industrial applications such as high-temperature furnaces and chemical processing equipment benefited from these advances in high-temperature resistant materials. The journey from early experiments with directional solidification to modern coated single-crystal component systems has been marked by countless moments of frustration, failure, and eventual triumph. Scientists and engineers have dedicated entire careers to refining every aspect of this complex process. Some have focused exclusively on developing new alloy compositions, systematically testing thousands of variations to find combinations that offer the ideal balance of properties. Others have specialized in the science of solidification, conducting elaborate experiments to understand exactly how crystals grow under different conditions and how this growth can be precisely controlled. There were also those who dedicated themselves to surface chemistry and coating development, facing the monumental challenge of creating layers that could permanently adhere to metallic substrates while withstanding brutal thermal cycles without failure. And we cannot forget the process engineers who transformed laboratory discoveries into reproducible manufacturing procedures, developing specialized equipment, control systems, and quality protocols that ensured each component produced would meet the rigorous standards required for safety-critical applications. One of the most remarkable achievements of this journey was the way different scientific disciplines had to work together. Solidification physics, the thermodynamics of multi-component alloys, high-temperature materials mechanics, surface chemistry, process engineering, computational modeling, all of these had to be cohesively integrated. It wasn't enough to be an expert in just one area. Success required interdisciplinary teams capable of understanding and contributing across multiple disciplinary boundaries. It was, in many respects, one of the first examples of the truly integrated and multidisciplinary materials science that has become so important in the modern world. The technical challenges encountered along the way were breathtaking in their complexity. Consider, for example, the task of creating ceramic molds that could withstand molten metal at temperatures exceeding 1,500 degrees Celsius. These molds needed sufficient mechanical strength to avoid collapsing under the weight of the liquid metal. They needed chemical stability to avoid reacting with the alloy and contaminating the final product. They needed adequate permeability to allow gases to escape during filling, but not so porous as to allow metal penetration. And they needed compatible thermal expansion to avoid cracking during heating and cooling cycles. Developing mold materials and manufacturing processes that met all these requirements simultaneously was a significant technical achievement in itself. Or consider the problem of measuring and controlling temperatures with the precision required for successful directional solidification. Temperature gradients on the order of hundreds of degrees per centimeter were needed, and these gradients had to be kept stable as the mold moved slowly through the furnace. Any fluctuation could result in the formation of unwanted grains or other defects that would ruin the component. Thermal control systems developed for this purpose represented significant advances in high-temperature engineering, with multiple independently controlled heating zones, sophisticated thermal insulation, and instrumentation capable of providing real-time feedback on the conditions inside the furnace. As the technology matured, a deeper understanding of the fundamental mechanisms that determined the success or failure of the process also emerged. Scientists discovered that minute impurities at parts per million levels could drastically affect the ability to grow single crystals. Unintended elements could segregate to the boundaries of growing crystals and alter their relative growth rates, favoring the formation of multiple grains instead of a single crystal. This led to the development of extremely sophisticated purification techniques and rigorous control of every ingredient that went into the alloy. It also became clear that the crystallographic orientation of the single crystal had to be carefully controlled. It was not enough to simply produce any single crystal. It needed to be oriented in a specific way relative to the component axis to maximize mechanical properties in critical directions. This required the development of techniques for controlled nucleation of crystals with specific orientations, a process that involved a detailed understanding of how different mold interfaces interacted with the solidifying metal and how initial thermal conditions influenced which crystallographic orientation was favored. Testing and characterization of single crystal components also presented unique challenges. Conventional materials testing methods were based on samples with polycrystalline grain structure and statistically average behavior. But single crystal components had highly directional properties, and their behavior could not be adequately predicted by standard testing methods. New characterization techniques had to be developed, including X-ray diffraction methods to precisely determine crystallographic orientation, advanced electron microscopy to examine microstructure at the nanoscale, and specific mechanical tests that could evaluate properties in different crystallographic directions. The learning curve for mass production of single crystal components was steep and expensive. Manufacturers had to invest millions of dollars in specialized equipment, personnel training, and process development before they could produce components with acceptable yields and competitive costs. Many early attempts resulted in rejection rates exceeding 50%, with components having to be discarded due to defects such as spurious grain formation, solidification cracks, or incorrect crystallographic orientation. But persistence and continuous improvement gradually increased yields until commercial production became viable. One fascinating aspect of this story is how it demonstrates the power of basic research to generate transformative practical applications. Much of the fundamental knowledge about metal solidification, crystal growth, and alloy thermodynamics was developed by academic scientists working on problems that seemed purely theoretical at the time. They weren't necessarily trying to solve practical engineering problems. They were simply trying to understand how nature works at a fundamental level. But when engineers faced the practical challenge of creating components for more advanced jet engines, they were able to draw on this reservoir of basic knowledge and apply it in ways its original creators may never have imagined. This synergy between basic science and applied engineering remains a recurring theme in the history of modern technology. The discoveries that make practical advances possible often stem from research conducted decades earlier by people who simply wanted to better understand the natural world. And the practical challenges faced by engineers frequently inspire new directions for basic research, creating a virtuous cycle of discovery and application that drives technological progress. Looking to the future, single crystal component technology continues to evolve. New generations of superalloys are being developed with increasingly complex compositions, incorporating elements such as rhenium in significant quantities to further improve high-temperature resistance. Additive manufacturing processes, or three-dimensional metal printing, are being explored as possible alternatives or complements to traditional casting, potentially offering greater design freedom and reduced material waste. Advanced computational techniques, including machine learning and artificial intelligence, are being applied to optimize alloy compositions and process parameters in ways that would be impossible through purely empirical experimentation. But regardless of how advanced the technology becomes, the fundamental principle discovered decades ago remains valid. Eliminating grain boundaries through controlled directional solidification allows materials to operate at much higher temperatures and withstand far more severe conditions than would otherwise be possible. This simple yet profound insight completely transformed what was possible in terms of the performance of jet engines and other high-temperature systems, and it continues to influence the development of new materials and processes to this day. The initial reaction of shock and amazement from American observers when they first saw what this unique process could accomplish was entirely justified. They were witnessing nothing less than a revolution in materials science and engineering. A revolution that would allow aircraft to fly faster, farther, and more efficiently. A revolution that would make electricity generation more efficient and less polluting. A revolution that would open up entirely new possibilities in countless applications where high temperatures and harsh environments were the norm. And perhaps the most remarkable aspect of this story is that it wasn't the result of a single moment of genius or a happy accidental discovery. It was the product of decades of hard work by thousands of dedicated scientists, engineers, technicians, and other professionals who each contributed, in their own way, to the gradual advancement of knowledge and technical capability. Each failed experiment taught something valuable. Each small improvement in the process contributed to overall viability. Each new understanding of fundamental mechanisms opened up new possibilities for optimization. This is the true nature of technological progress. Not magical leaps into the future, but rather the patient accumulation of knowledge and skill through sustained effort over time. The monocrystalline components that are now routinely produced and that power the world's most advanced aircraft are the cumulative result of countless individual contributions, each building upon what came before, each pushing the boundaries a little further. For observers who have had the privilege of following this journey from the beginning, it must have been an extraordinary experience. To see the transformation from the first alloys that could barely withstand the basic operating conditions of primitive jet engines, through successive generations of increasingly capable superalloys, to finally witnessing the emergence of monocrystalline components that could defy temperatures that would have been considered impossible just a few decades earlier. It is a testament to what humanity can achieve when it applies intelligence, creativity, and determination to the challenges it faces. As we conclude this exploration of how a single industrial process enabled alloys to defy extreme temperatures, it is worth reflecting on the broader lessons of this story. It reminds us that the limits of what is technically possible are constantly redefined by human ingenuity. It demonstrates the immense value of basic scientific research, even when practical applications are not immediately obvious. It illustrates how interdisciplinary collaboration can lead to advances that no single discipline could achieve. And it shows us that real progress requires not only brilliant ideas, but also careful implementation, patient refinement, and a long-term commitment to excellence. The single-crystal turbine blades that spin inside modern aircraft engines are much more than just mechanical components. They are symbols of humanity's ability to understand and manipulate matter at a fundamental level, to transform theoretical knowledge into practical technology, and to overcome challenges that initially seem insurmountable. Every time an aircraft takes off, every time a gas turbine generates electricity, we are witnessing the practical application of decades of research and development in advanced materials. And so, when those American observers first saw how a single industrial process had enabled metal alloys to withstand the extreme temperatures of critical operating environments, they were not merely witnessing a stunning technical innovation. They were witnessing the culmination of an extraordinary journey of scientific discovery and engineering achievement. They were witnessing proof that apparent limits can be transcended through deep understanding and intelligent application of the fundamental principles of nature. They were witnessing, in short, one of the great triumphs of modern science and technology. May we continue to pursue knowledge and excellence with the same dedication shown by the pioneers of this remarkable technology. May we face the challenges of the present and the future with the same combination of scientific rigor and engineering creativity that made this revolution in high-temperature materials possible. And may we always remember that truly transformative advances rarely happen overnight, but are built patiently, step by step, through the collective effort of many dedicated individuals working towards a common goal. May the Lord God bless the efforts of all those who dedicate their lives to the advancement of human knowledge and the development of technologies that benefit humanity. And may His wisdom continue to guide us as we explore the mysteries of creation and seek to use this knowledge to improve the world around us.